first let me say thanks very much to the organizers for putting this nice workshop together, for organizing this longer meeting, and also for giving me the opportunity to talk about some things I've been thinking about. So what I'm going to be telling you about today is some stuff connected with symmetries, more specifically generalized symmetries, and how to apply it in the context of certain non-supersymmetric backgrounds in string theory. What we've kind of developed over the past couple of years is a set of tools to understand how generalized symmetries can be both computed and extracted and studied in supersymmetric string backgrounds. And then a very natural question is how much of that carries over to more general backgrounds. Okay, so whatever. Okay, so this is going to be based on a paper which will hopefully be finished soon. It's with two graduate students at Penn, Noah Brigger and Vivek Chakrabarti, as well as a postdoc, Max Hubner. Okay, so it's also based on a set of papers written over the last few years, hopefully I didn't forget anybody, involving permutations of this set of authors. I'll review a little bit of this, but I won't kind of go into too much detail about all of it. Okay, so I guess I might be the first person talking about symmetries in this context. So symmetries, what are they? I think you know. They're interesting. Well, I find them interesting. They're also very useful when you can find them. For example, in the context of, say, selection rules, constraints on RG flows, things like this. So these are all, there's many other things you can talk about in these contexts, but I think it's pretty clear that symmetries have been very helpful in many contexts. And recently, there's been a kind of recent generalization of what we mean by symmetries, both in the context of both physical and mathematical structures. So I'll briefly review a little bit of that. My aim is not to kind of go through every single detail of this, because I probably can't, but I just want to kind of set a couple of the terms that I'll be using later on. Okay, so generalized symmetries were introduced in the context of quantum field theory in this very nice paper. And if you like, the main slogan of it has to do with saying that there's a topological character to global symmetries. So when we say that we have, say a local operator, O of x, and we're acting upon it by a symmetry, let's say G times O or something like that, there's a way of visualizing this in terms of some codimension d minus 1, my quantum field theory is in d spacetime dimensions, as linking with that point-like object. So when I try to drag it through or shrink the thing down, there's a notion of the symmetry acting upon the operator. So here, this is what we kind of refer to as the kind of conventional textbook, so-called zero-form symmetry. Now, once you have this, of course, we can start playing games with not necessarily local operators, maybe extended operators, maybe different kinds of symmetry operators. So for example, if we wanted to talk about, say, a one-form symmetry, we could talk about, say, a line operator, and then a d minus 2 dimensional object which links with it. So the key idea is that the dimension of this operator that's charged under the symmetry operator, the dimension of those supports adds up to d minus 1, so that they maintain a topological linking. You can do slightly more general things where, say, zero-form symmetries can act on lines and so on, but this will be okay for, I think, today. So we refer to this as, say, a one-form symmetry. Okay, and I think you can spot the pattern. You can talk about p-form symmetries now if you had, say, a surface operator, let's say d minus 3, and so on. Okay, so there's many generalizations of this which have been explored recently. Here's just a few. So the one I just told you about is higher p-form symmetries. You can ask about entwinements between the different zero forms and one forms. So sometimes zero-form symmetries can act non-trivially on the lines and so on. These can form so-called higher group structures. And you can even ask what happens if we start bringing some of these topological operators together. Do they always form, say, a group-like composition, or do they form something a bit more general? So for example, when you take product of them, does it make a third one in the group, or does it produce, say, a sum over these things? This would be what we refer to as a non-trivial fusion rule. And so it's kind of an active area of investigation to figure out what is the actual, if you like, categorical structure that these symmetries obey. What's been done at this point is kind of just building lots of very nice examples. I don't think there's a completely well-understood framework for how this works in more than 2 dimensions. Okay, so string theory, where does this enter the game? Well, it's very helpful in the context of studying these generalized symmetries, especially if we want to consider so-called non-Lagrangian or more general kinds of quantum field theories. So we now know from various string constructions that we can make conformal fixed points in more than 4 dimensions. It's very difficult to access these things using, say, conventional Lagrangian techniques, but we can nevertheless build them, and we can also study their generalized symmetries via methods I'll briefly review a little bit later. And of course, if you take these higher dimensional fixed points, there's no known Lagrangian for any of these. If you start compactifying them, then you get examples of what are sometimes referred to as like non-Lagrangian quantum field theories. So even if you had a Lagrangian, it may not be the most helpful thing to possess. And then another kind of natural thing to talk about in this context is, suppose somebody hands you one of these interesting generalized symmetries in this context. What happens if you switch on gravity to all these nice topological structures? Do they survive? What becomes of them in those kinds of limits? I'm not going to talk about all this. I'll kind of just briefly sketch a little bit of that. But the one thing I do want to stress for right now is that the bulk of these analyses, at least all the ones I know about, when we try to do this in context of embedding in string theory, typically rely on having supersymmetry in the game. And we're doing this for very good reasons, because we're trying to maintain control. I don't know how to build a higher dimensional fixed point, for example, without supersymmetry. But that's one of the things that's kind of baked into the general recipe. So of course, you know, look around you. It's not supersymmetric around the world. So you might ask, can we do any better in the context of, say, strongly coupled systems without supersymmetry, and compute generalized symmetries in those contexts from a top-down point of view? Okay, so what about non-supersymmetric backgrounds? I already said this. No superpartners have been seen yet. I'm probably more optimistic than most of the folks in this room. But okay. So one question is, can we build a robust non-SUSY tool? So of course, when we have a Lagrangian, there's various effective field theory methods. But when you're at strong coupling or more general kind of stringy backgrounds, what can you do? And the main idea, or the main thing I'm going to be exploring today, is whether we can leverage things we know about topology in the context of the extra dimensions of string theory, and how that feeds down into symmetry structures in kind of the uncompactified directions. So the plan for my talk is I'll first kind of review how it works in the supersymmetric setting. And then what we're going to see is that many of the elements that we have here naturally carry over to the non-supersymmetric case. And then I'll just summarize and explore a couple interesting future directions. So I'm going to now move on to explaining what we think we understand about the supersymmetric case, and then why it looks very plausible that it extends over to the non-supersymmetric case. Okay, so here's the typical supersymmetric setup for engineering, say, a quantum field theory. So this panel over here is the kind of quantum field theory that we're interested in. We're going to place this on a non-compact background. So Newton's constant has been set to 0 in the d-dimensional spacetime. Of course, you still have, say, the 10d or 11d g Newton. And all the quantum field theory degrees of freedom are kind of concentrated in a little singularity. This can happen because, for example, open strings can attach to a brane and they can't float away, but a closed string, for example, can just move around. Okay, so I'll be a little bit loose in what I call a singularity. This could refer to any, say, curvature singularity or, say, a brane probe, anything like that. Now, how do we get, say, our line operators and our symmetry operators in this setting? Well, we can start playing games with branes. So if we wanted to put, say, a heavy defect into the system, what would we do? We would wrap a brane. It would kind of fill out a non-compact cycle, so one that stretches from the tip of the cone, where we have this thing, out to what I'll refer to loosely as infinity. So this is kind of like the boundary of this non-compact space. And then some number of the dimensions will just be eaten up by wrapping it over some cycle, but then some of those directions will just kind of float around inside of the quantum field. So this is a way for us to engineer, for example, line operators, surface operators, and so on. How about the symmetry operators which act upon those things? Well, they have to link in some way. The case I'm going to focus on primarily is the one where it's a discrete symmetry, but I'll sketch how it goes for more general, say, continuous symmetries. So there has to be a linking, it turns out, between both in the space-time as well as off in the boundary. So there's a brane that we're introducing, which is going to engineer for us the symmetry operator. And the key idea is that it's maintaining a topological linking both here and here, so that when we drag it through, what ends up happening is the heavy defect gets acted upon. So if this is, say, a Q brane, then on the red thing, then the blue one is going to be enacted by a magnetic dual P brane. And we wrap these on the cycles. And one can check that this does enact the correct linking in terms of how the symmetry operates. Another important point is that this thing is really topological, so we can wiggle it around. It doesn't really do anything. And it doesn't impact really what's happening at the quantum field theory because it's very far away from where all the interacting degrees of freedom of the singularity are sitting. So whereas the defect, of course, has to stretch from the tip of the cone out to infinity, symmetry operator is very far away from that action. So the only thing it can do is kind of topological type linkings. Okay, so how do we actually calculate things like the higher form symmetries in this setting? Again, I'm not going to go through the whole game, but I want to at least sketch a piece of it. So a little more technically, if somebody hands you a heavy defect, there's no guarantee that it just comes with a continuous p-form symmetry. Some of the symmetry might be screened, a la Tuft. So how does this happen? Well, there could be dynamical, or there are dynamical states in the quantum field theory, which can terminate various lines or surfaces and so on. So what we're going to do is we're going to talk about branes that wrap a, say, k+1 cycle like this, and I'm denoting it like this to just indicate that it's allowed to terminate on something at the boundary. And it can be partially screened by the dynamical states, which are captured instead by looking at, say, compactly supported k+1 cycles. So the field theory characterization is just that, well, we have some line and it gets terminated like this. The thing we have to calculate is then some quotient of this form. So there's a natural embedding of all the compact things into these relative cycles, if you like, and we just have to start calculating these kinds of quotients. Now, this can be systematized a bit because you can say, well, which cycles should I talk about? Which Q-branes should I talk about? In principle, you should talk about all of them. And so this is called calculating a thing called the defect group. So we just sum over all the possible choices of the quotients and then all the possible choices of the Q-branes. The main condition we have for the Q-branes is that they must carry some kind of conserved charge. This is just to make sure that we have something to talk about in terms of a defect. It might be something like a Ramon charge, but it could be something a little more fancy involving, say, a discrete K-theoretic charge, which is just a discrete remnant. Okay, so that's a very nice story, and it was worked out, I guess, about, well, there's an earlier paper that introduced this notion, and then many of the details got fleshed out in, or exactly how to apply this for p-form symmetries got fleshed out, especially in this paper and this paper. Okay, now how about the symmetry operators? I already mentioned this, but I'll just say it again. We just need the magnetic dual branes linking. In the case of discrete symmetries, it turns out to just be the ones that are linking both in the spacetime and in the boundary geometry. For continuous symmetries, it's a slightly more subtle question. You have to deal with what's called a flux brane, which you can think about as basically like a capacitor model with, say, a brane, anti-brane, which have been separated, and then there's some amount of flux. The dynamics of that thing tells us about the associated continuous symmetry. So that's a story that's very nice, but that's not the focus for today. I'm now still just reviewing things that have kind of already been worked out. Okay, so now how about gravity? Just compactify, but one of the interesting things you can see is that automatically, by the way we built this thing, we can start tracking the fate of defects and symmetry operators. So remember, initially this thing was off at infinity. Once you glue into a compact geometry, all those branes will start to become dynamical in various ways. So we can watch what happens and see whether they embed inside of a genuine cycle in the compact model, or whether they just become topologically trivial in the full compact model. So the key idea, though, is that all the symmetry operators and defects are becoming dynamical, fluctuating things once we start coupling to gravity. And there's a nice complementary story I should mention holographically, where you can also see the symmetry operators become dynamical. Okay, so let me just illustrate some of this in a particular example. So let's take a particular geometry. So I'll take C3, and then I'm going to quotient by a finite subgroup of SU3. So if you need an example to hold on to, just take this to be, say, Z3 with just third roots of unity along the diagonal. So here, maybe I realize I didn't write this down. Where omega is just so this is the group action for C3 mod Z3. If somebody tells you they're taking a quotient, they have to tell you two things. One is the group, and the other is how does it actually act on the space. Here I'm telling you. And this one will turn out to preserve supersymmetry. But you can do it more generally for any finite subgroup of SU3, and it turns out you'll always preserve supersymmetry in that case. The reason is that the holomorphic 3 form will be invariant under that group action. Okay, so here's a picture of the topology. So if we work in, say, polar coordinates or radial coordinates, we have, say, a boundary generalized lens space where the group action from C3 induces an action on the boundary 5 sphere. And then there's some radial direction that kind of extends out from the tip of the cone out to infinity. Okay, so let's just give an example of how this goes. Let's imagine that we had type 2A string theory on this background. What would we get? Well, we would get, if you like, a 4D n equals 2 SCFT, which is typically going to be strongly coupled. You can view this as actually the M theory reduction of or the circle reduction of a 5D superconformal field theory. We can start with this particular singularity in C3 mod gamma and M theory, and then we can track and see what happens to this thing as we go down on the circle. Now, how come we think it's a CFT? Well, if you resolve this geometry, what you typically find is 2 cycles and 4 cycles. So let's assume that we had such 2 cycles and 4 cycles which were collapsing. What would we see from the perspective of the 4D effective field theory? Well, we would start seeing electric states from, say, D-branes wrapped on, say, a collapsing 2 cycle. That's what this picture is supposed to indicate. So here I'm indicating the 4D spacetime and then the kind of extra dimensional stuff. So we can wrap, say, on a 2 cycle here or, say, a 4 cycle here. Now, if we wrap the 2 cycle, then we get, say, an electric state, and the magnetic dual one gives us the 4 cycle. And the key point is that we have simultaneously light electric and magnetic states. This is one of these hallmarks of having an interesting interacting fixed point. And we're preserving n equals 2 supersymmetry. Why? Because we can count the number of killing spinors that are left over in this kind of background. Okay, so that's just, let's engineer the field theory. Now, how do we see the defects and the symmetry operators in this setting? Okay, so I'm going to switch from this kind of nice holomorphic presentation to one that emphasizes the boundary 5-0 mod gamma. So the idea is that we have that radial direction, which goes from the tip of the cone out to infinity. That's this 4 direction. And then we have the 5, 6, 7, 8, 9 for the generalized lens space. Now, the line defect we can engineer is just given by wrapping a torsional 1 cycle of the D2 brane and then this radial direction here. And this gives us a heavy line defect. What links with that? Well, the magnetic dual thing is a D4 brane, and we can wrap it over here. This will, you can notice that the dimension of this plus the dimension of that adds up to 1 less than 4. And then we can wrap this again on a torsional 3 cycle, which links with that 1 cycle. Okay. So one of the nice things about this is you can also read off non-trivial fusion rules if they're present by just taking the topological terms of, say, the D4 brane and then just dimensionally reducing them on the torsional cycles we have in this setting. So it provides a basically algorithmic procedure for reading off interesting fusion rules in this class of theories. Okay, so now how do I calculate p-form symmetries in a little more detail? I'm not going to go through the fusion rule story today, but how do you get like basic things like p-form symmetries? Well, there's kind of 2 approaches which are very complementary to one another, and we can make this much more precise. This screening effect, where you take relative cycles which stretch out to this, modulo compact things, it turns out that that can be replaced by just a computation of things having to do with the homology groups of the boundary generalized lens space. So if you know how to calculate this thing, you basically can calculate that defect group and correspondingly the candidate p-form symmetries for the system. There's another related way, which is just say, well, I just want to know about heavy lines in the theory. Why don't I just look at probe states and possible Dirac pairings of that? It turns out that that's a complementary way, which is gives you identical information to this. This goes under, if you like, the generalized Mackay correspondence, where things you know about this, and you're encoding intersection theory data about what's happening in this geometry here, and in particular the boundary generalized lens space. Okay, so this one here, let's compute it. Okay, so if you can calculate it in generality, and for any gamma, it doesn't even matter whether it has fixed points or not. You can calculate it in all these cases. There's a very nice theorem by Armstrong in the 60s, which showed that basically this thing is just captured by the original gamma you had, and then you quotient by a normal subgroup, which is capturing all the fixed point stuff. Taking the abelian, this actually calculates the pi 1 of the space. Taking the abelianization gives you the h1 of the space. This is a thing that can basically be done in all examples. And let's suppose that there were no fixed points off at the boundary phi sphere. Then, just to give you a clean example, you get something like z mod n. So it can be done basically for any non-abelian, doesn't matter what. So we can get a candidate answer for what the one-form, say, electric symmetries are. So reading off h1. If we want to know about, say, in a different presentation of the theory, where we had, say, the magnetic one-form symmetries, we would talk about h3 instead of h1. Okay. How about the quiver approach? So there's a very nice paper from, I guess, a couple of years ago now, where they observed that if you want to read off the exact same A data, it's enough to know what the Dirac pairing is for electric and magnetic states of the theory. So as long as you know what the electric and magnetic states are, that is enough to start reading off the exact same information. Morally speaking, the reason is that what we do is we start winding these heavy lines around each other, and we can expect them to experience a non-trivial phase, depending on what the electric and magnetic charges are. And okay, there's this kind of imposing looking formula, but the basic idea is that there is a Dirac pairing that you get. That's what this thing is supposed to indicate. You basically look at the space it maps into, quotient by the image. That's what the co-kernel is telling you. And then you take the torsional bit of that, and it reads off for you electric and magnetic candidate one-form symmetries for the system. And in fact, you can check that the two methods match. Let me just illustrate how that goes in one example. Let's say we took a D0 brane probing our friend C3 mod Z3. What will we do? Again, this nice picture, we can actually read off the Dirac pairing directly from, say, the adjacency matrix of the quiver. So remember, in a quiver, we have, say, a basis of fractional branes, the image branes, if you like, under the group action. And then we have open strings which stretch between those fractional branes, or those image branes. Once you know that adjacency matrix, you can form an anti-symmetrized version of it. That thing is the Dirac pairing for this 4D theory. And all you have to do is then, once you have that matrix, basically calculate this thing. It's convenient sometimes to go to so-called Smith normal form, but it's not crucial for anything I'm telling you. You just have to calculate this. And you can read off directly that you get a Z3 electric one-form and a Z3 magnetic one-form symmetry. So basically the upshot of this is that the world volume theory of a probe D0 brane, looking at this kind of singularity, knows about the electric and magnetic one-form symmetries. And we can actually relate this again directly to the homology of the boundary space. Okay, now this was all in the context of type 2a. There's a very similar story you can tell if we switch over to type 2b. Say, well, I saw a D0 brane. Why don't you wrap on a T3 and T-dualize? You can do the same thing for a 4D n equals 1 SCFT now, where you now have a four-dimensional quiver gauge theory. This is what the 4D quiver gauge theory looks like. And then if you T-dualize all the defects I told you about, then you get a nice story involving, say, now, two-form symmetries, surface defects, and the symmetry operators that act upon them. There's more to say here, but this gives a rough idea. In fact, one of the nice things you can do here is there was some very nice work done on the field theory side, looking at so-called duality defects in n equals 4 Yang-Mills. I couldn't fit all the references cleanly, so I'm sorry that they're so small. But there's been a lot of interest in doing this, both from the bottom-up, if you like, field theory side, and also from the top-down side. But from the point of view of what we're doing here, all it requires us to talk about is a particular codimension 1 defect associated with a 7 brane with a constant axiodilaton which wraps that generalized lens space. This thing is enacting a particular symmetry operator in the 4D field theory. This works fine both for n equals 4 Yang-Mills, but also for different kind of quotients which preserve n equals 1 supersymmetry. And these folks here wrote down some very nice examples illustrating the fusion rules. You can also see a lot of that structure just pop straight out from looking at how the dimensionally reduced 7 brane actions behave when you fuse them together. Okay, so that's all I'm going to say right now about the supersymmetric case. Now I'm going to start switching gears and start talking about what happens when we don't allow ourselves supersymmetry. When did I start?
About 2 minutes past 9.
Okay, very precise. All right. So now let's turn to the non-supersymmetric case. Now, okay, you might ask, how much of this lovely structure still works if we start breaking supersymmetry? Okay, so we have different kinds of ingredients. First of all, we're talking about engineering a singularity. Second of all, we're talking about having some heavy defect. And then third of all, we have some symmetry operator. Now, the reason to be optimistic that some of this will work is that the symmetry operators in particular are way off over here. They're very far away from the dynamics or the things that are happening at this singularity. So we can expect that something will happen to the singularity. Maybe it will, resolve in some nice way. But that stuff is going to take some time to get out to so-called infinity. So we're expecting that the symmetry operators are kind of going to be quite robust against anything that we did kind of locally in the interior of the space. Nevertheless, of course, the kind of localized degrees of freedom here are going to start jumping around on us. And even the defects, which are experiencing that localized geometry, we expect those to also kind of possibly experience what is happening with the singularity. Okay, so I've already said this, but I'll say it again. We're going to engineer a so-called local system, the singularity. Definitely that's going to change. The defects will probably change just because they know about the singularity. But the symmetry operators, which are very far away, will not change. Okay, so I'm going to basically illustrate how this goes. And this is the purpose of the upcoming paper, how this goes in a particular non-supersymmetric orbifold, which is illustrating many of the same features we talked about. Okay, so I probably missed some references, I'm sorry. But what I'm going to do is talk about, okay, it's no longer supersymmetric, so I'm just going to write R6. And I'm going to say I'm going to quotient by a finite subgroup of SU4. Even this is a little bit vague. To really tell you what I'm doing, I need to tell you how I'm acting on both the bosonic and the fermionic degrees of freedom. Since we're not in a supersymmetric world anymore, I have to specify each independently. But that's not a big deal. We can do it. And in particular, we're going to pick it, the group action, in such a way there's no killing spinner left over. So as long as we pick a finite subgroup of SU4, which is not embeddable inside of an SU3 subgroup, then we're kind of guaranteed to lose all the supersymmetries. Just no supersymmetric zero mode left over. And I'm going to assume, for the purposes of this discussion, that the singularity is isolated. But you can actually relax that. It doesn't affect the analysis really at all if you allow a singularity to also kind of extend out to infinity. Just means that there might be other kind of tachyons present. Okay, so type 2 on this kind of singularity, there's a localized tachyon in one of the twisted sectors, generically. Let's assume that's the case. What will start happening? Well, there's some nice work by folks in the room, I don't know where you are, who actually analyzed this and explained precisely what happens as a function of time. So you get this twisted sector closed string tachyon, and it starts eating up the original singularity. It leaves behind kind of a milder or less singular thing in these cases. There still is a geometry here. It's not like a bubble of nothing or anything. There's still a geometry here, but it's smoothed out in some way. It might be totally smooth, or it might be just a supersymmetric singularity in many cases of interest. Okay, and here it goes. So what is happening at the level of just the geometry? Okay, so here's my picture for what's happening at early times. We have the defects, the symmetry operators, they link. That's very nice. And then as we expand out, I'm trying to indicate both how the geometry changed a little bit and how the defect changed. Symmetry operators don't care. What we're going to do is we're going to try and calculate the p-form symmetries again. Now you might say, oh, well, this is trivial because nothing happened at infinity. Well, it depends on what you want to call infinity in this context, right? So there's the original infinity, prior to anything exploding out. But maybe I wish to redefine what I meant was infinity after some resolution process has taken place. Usually one can track stage by stage how the different tachyons are condensing. And so we can change our notion of infinity also as a function of time. So we can calculate jumps in, say, the p-form symmetry as a result of shifting. So maybe I don't like my infinity being here. Maybe I want it to be down here somewhere. Okay, so let's recalculate everything in this context. Okay, so I'm going to basically follow the exact same approach we did before. I will talk about the boundary homology, S5 mod gamma. That Armstrong's theorem, by the way, doesn't care at all about holomorphic structures or anything. It's just a topological fact. And then we'll do it again via the quiver approach, where we just say, I just want to know about what's happening to probe particle states as I move them towards the singularity. I'd like to know what's happening to the electric and magnetic one-form symmetries. Okay, so let's go ahead and calculate that. Isn't they? So we have this thing here. Let's go ahead and calculate it again. Basically, absolutely nothing changes. It's the exact same computation. The only thing that changes, of course, is the choice of group and the fixed point locus. It's an identical calculation at that level. So again, if you had, say, a fixed, if you had z mod n, so in this case, where it was, so as a nice example here is, let's do R6 mod z5. And I'll specify how it works on the 4 of SU4. Well, you can take it to be omega, 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 omega minus 3, where omega is just e to the 2 pi I over 5. So once you know how it acts on the spinor representation, it induces a corresponding action on, say, the geometry on R6. Okay, thanks. So we can read off what's going to happen in that case. In this particular case, it's again just a Z mod 5 electric one-form symmetry. You can do the same business for H3. Same deal. It works for everybody. Like non-abelian, abelian, doesn't matter. How about over on the quiver side? Okay, well, I do exactly the same thing. The argument presented in here, and as we're going to do here, doesn't really care about the amount of supersymmetry. The main point is that if you knew enough about the Dirac pairing, then you would have enough information to start reading off the electric and magnetic one-form symmetries. So I'm just going to do the exact same thing. I'm going to talk about probe states in this singularity and see what I get. Okay, so this is basically just a copy-paste of the previous slide. The only thing that changes now is this begs the question, okay, now how do you read off the Dirac pairing? Now, it's not 100% obvious from what I've told you, and the reason the Dirac pairing is not 100% obvious is because since we're dealing with a non-supersymmetric quiver, there's actually two notions of adjacency matrix we might want to talk about. There's the ones associated with, if you like, the fermionic degrees of freedom, and there's the ones associated with the bosonic degrees of freedom. So I actually have two adjacency matrices I can, in principle, talk about in this setting. So hopefully this balances out the quote from earlier, if you're so inclined. All right, so here's the Dirac pairing. We have a D0 brane at a singularity, and it turns out that the Dirac pairing is just captured by the fermionic adjacency matrix. So we can calculate that thing. We can actually just go through the quiver quantum mechanics to double check this. It's just basically you ask, what is the response of winding one of these things around the other? You just look in the world volume theory of the quiver quantum mechanics and track to see whether a Berry phase is picked up in the corresponding ground state wave function. The fermions are basically the only thing that can induce a non-trivial phase. The bosonic degrees of freedom are essentially spectators from that point of view. So the only thing as far as this goes that I need to pay attention to is actually the fermionic adjacency matrix. So again, these are open string degrees of freedom, and in the spacetime they have fermion number non-zero. Okay, so now let's compare our answers between this and the geometric approach. They don't actually completely agree, which is not totally shocking because it's not supersymmetric. The quiver answer actually provides a refinement. So it has all the geometric stuff. We can check that explicitly in loads of examples, but there tends to be like a residual remainder term. We don't actually have a great geometric interpretation of this extra stuff. It's not shocking, though, again, because the quiver kind of knows a little bit more than just the boundary homology of the space. Okay, so we can actually now read off the electric and magnetic one-form symmetries for this setting. Okay, so now if we go back, we can, again, ask what is happening here. So all I told you is basically at early times. Now, at late times, our notion of what we meant by infinity is changing. The singularity is completely changed. We can, again, say what happens to the branes probing that kind of singularity. So we can recalculate, if you like, this defect group as a function of time. And we're basically doing a step function approximation where we say, what does the quiver look like at early times? What does it look like at late times? And we keep going from that point of view. Okay, so in this example I just told you about, R6 mod Z5, the early quiver looks like this. And then at late times, it's just a D0 brane exploring flat space. Okay, so we can actually do that. There's a very nice story also to tell about a so-called symmetry topological field theory that goes along with this, where you can actually check as a function of time how that topological field theory is jumping. And so there's basically levels in that theory that are jumping. I'm going to skip that and move instead on to the case of D3 branes probing the same exact singularity. So again, we have this kind of picture. Now the story is more dictated not so much by time, but by energy. And we're imagining that, say, well, perhaps the singularity starts to roll out in some way. But modulo that, I can, again, track exactly the same degrees of freedom. I can track what happens to the different surface operators, the defects, and so on. Okay. And I can watch what happens as these things expand out. So again, it looks basically like the same picture. It's now just as a function of, say, energy scale. Okay, so now what I'm going to do is explain how this connects to, so of course, folks have been looking at this thing for a long time now, these kinds of systems for a long time now. How does it relate to that stuff? Okay, so my understanding of how it goes is that it looks very promising to get, say, a fixed point if you, say, look at single trace operators and 1 over n, especially in the planar limit, but double trace operators appear to spoil that. And there's a nice correspondence, in fact, behind finding that there's certain double trace operators which are not flowing to a fixed point, and that corresponding twisted sector closed string tachyon, having a closed string tachyon in a particular twisted sector. And you can make this more precise. Folks have also looked at, say, radiative corrections and associated Coleman-Weinberg potentials that get induced. And all of this matches up pretty well with that. The thing that we hope to do in the future, but it's a little bit murkier, is this boundary S5 mod gamma. You might say, well, if I took the near horizon limit, say, of a stack of D3 branes, perhaps I get an interesting non-supersymmetric background like ADS5 times S5 mod gamma. That sounds very promising, but these folks here found that there's basically an analog to a bubble of nothing, which appears to eat up part of the solution. So it's not totally clear what the relation of that is to the perturbative closed string tachyon, but it's very suggestive. And in particular, the fact that the only thing we cared about was the boundary topology suggests that we could make a more precise link. It's just tracking as a function of the 't Hooft coupling. What is happening is we go from small to, say, large values. So it's something we hope to do in the future. Some other structures I didn't mention, but they're there, and we'll mention them in the paper. There are things like these higher groups. I didn't really talk about it, but it turns out that this happens whenever certain properties of the non-abelian group appear, in particular when this short exact sequence doesn't split. That's in the 2A case. In the 2B case, these duality defects I told you about from n equals 4 Yang-Mills, you might ask, how do they get inherited down in this non-supersymmetric setting? They have a role to play in that setting as well, and you can actually watch as a function of the kind of tachyon exploding out, things that get dragged past the duality defect, and they produce new kinds of duality defects attached back in this non-supersymmetric setting. Okay, so I think I'm almost out of time, so I'll sum up and talk about future directions. So what did I tell you about? So I reviewed this branes at infinity picture for how to engineer symmetry operators in the context of various kinds of quantum field theories and so on. But one of the things I want to stress is that because they're off at infinity, supersymmetry doesn't really play any role. What we found is that the quiver answer that we got in the cases we looked at refined the geometric answer, and by that I just mean the boundary homology. There's most likely a more sophisticated geometric statement to make, which matches it spot on. I'd be shocked if there wasn't. Things that I'd like to do in the future, well, one of them is to just revisit what happens in the near horizon limit of a bunch of D3 branes at this thing, especially when the 't Hooft coupling is very large. The symmetry operators, at first glance, don't seem to care too much about what the value of the 't Hooft coupling is. So can we revisit, if there is a gravity dual, what does it look like? Or if there isn't, can we track like whether there's a possible phase transition as a function of the 't Hooft coupling? And of course, another very natural direction is just look at more general non-SUSY backgrounds. So that's it. Thanks.
Thank you very much.
Okay, thanks a lot for the really interesting talk. On this kind of last subject and the last question you're asking here, one way to use these theories that end up flowing because of the twisted sector, couplings, is as an effective theory. So it can be UV completed by something, up to and including gravity. It can be, say, part of a warped compactification, and then the, instability that I guess Gary and company stressed is then becomes, a very slow, non-perturbative process. So I guess my question is, in that scenario, how do these symmetries that you explained are sort of associated with the UV, or parts of them are? Right. Can you preserve some of that?
Yes. Well, so we've done that analysis in the supersymmetric case. We obviously haven't done it in the non-supersymmetric case, but the picture is here.
Yeah, exactly. So I mean, you can.
So to answer your question, the thing that we did in the supersymmetric setting was to ask, basically just using the Meyer-Vittoris long exact sequence for cutting and gluing. You can take things you know about local homology groups and then say, now how do they glue into a compact geometry?
Right.
And then you can say, well, did the p-form survive? Did p-form symmetry, did it survive in the theory coupled to gravity? Sometimes you do get a gauge p-form symmetry, and you can just compute it in using Meyer-Vittoris. So a very natural question is, it's one of the things we aspire to do in the future, say, all right, now what if it was a non-supersymmetric thing? Meyer-Vittorius does not care about supersymmetry at all.
Right.
Why don't we just redo the gluing in that case? Can we see a p-form symmetry survive in the non-supersymmetric setting? So that's absolutely one of the things we want to do. Yeah.
Okay.
Yeah.
Perfect. Thank you.
So there are known lists of quantum subgroups of both SU2 and SU3. I wonder, in your SU4 case, do you have such a list, or are you just doing the scattering?
Well, what we did is we have a general statement for it doesn't seem to matter what choice of non-abelian group or whatever, but actually the examples we took were from your paper with Ronan, and so most of the ones we took were just for the explicit example were just with the form Z mod n with specific group actions, and the reason why we did that is we wanted to be able to track explicitly the tachyon condensation. So you guys already wrote down for some of these models explicitly the toric geometry, how everything resolves. And so using that, we can say, I know exactly as a function of, say, energy scale or time, what happens to the defects by just recomputing.
So you're not doing non-abelian groups?
Well, the statements apply more generally. But so what we can do more generally is just say, for any non-abelian group, we can calculate H star S5 mod gamma, and we can also calculate the Smith-Normal form for the adjacency matrix of the quiver. That doesn't require any knowledge of basically any particular choice. But yeah, for the explicit examples, indeed, we basically focused on abelian ones. But if you know a good list of fun. Yeah, all right. Yeah. Yeah.
You had a slide where you had D0 branes and a C3 electric and magnetic form symmetries, or one form symmetries, or something like that?
Yeah, they're actually not both simultaneously realized, if that's where your question's going. There's a boundary condition you pick, and you get one or the other. Yeah.
I see, but they are just ordinary global symmetries of this D0 brane theory.
Well, those are the one form symmetries of the 4D system.
Okay.
Does that make sense?
Okay, so the D0 branes are charged under these symmetries?
Correct.
Okay, fine.
Yeah, exactly.
Okay.
So if there are no further questions, let's thank Jonathan again, and maybe Veronica.